Okay. Hello, everyone. Welcome to the NAGT webinar series. The NAGT webinar series is your one-stop shop for strengthening work in Earth education. Webinars in this series feature novel, innovative work in Earth education research and pedagogy, new teaching materials, and the classroom and professional experience for people like you. That NAGT webinar series is free and open to the public, and we encourage you to invite your colleagues to attend and join the discussion. In a few minutes, I'll put a link to the full webinar series where you can find the webinar schedule and future events, and then I'll mention the upcoming events toward the end. And this webinar is about geochemistry databases as an entry point into working with big data. And this is going to be led by Karen Block at CUNY, the City College of New York, and Dory Farthing at SUNY Geneseo. And from there, I'm going to turn it over to Karen and let her introduce things and get us moving.
Thank you so much, Rory, and thanks to all of you for taking the time to join us today for this webinar. We hope that it will be helpful and that if it will enhance and enrich your teaching practice so that we can stay current on making our students well-equipped for research and the workforce. My name is Karen Block. I am a professor at the City College of New York in Earth and Atmospheric Science, and so I will move on to the first slide. Oh dear, what's happening? Hold on. For some reason, my slide is not advancing. My apologies. Okay, here we go. It's my first time using PowerPoint, apparently, or any other slide platform. Again, my name is Karen Block, and I'm at the City College of New York. And my colleague who will be coming in for the second half is Dr. Dory Farthing at SUNY Geneseo. And we are going to be talking today about how we can use these really wonderful data resources as tools to teach about data in the classroom. And so roughly our outline will entail having a little introduction about what these databases are all about and why they exist in the first place, how you can access geochemical data. We'll give you some basics, and then hopefully you will go in and explore on your own. We will talk about working with data, and Dory will take over at this point to talk about the value for the classroom and some possible activities that you can engage in and some of the student reactions to working with these databases. And then we will wrap it up with a little talk about the future of the databases, and we ask you kindly to fill out the evaluation if you have the time. So why are we working with data and using databases? Well, as you saw in the announcement for the webinar, we know that working with big data is important to all students, right? Not just geoscience students, but all our students are going to be required to be competitive in the usage of data as they enter the workforce. And the thing that we realize is that over time, the tools will evolve, right? So right now we're in this Python moment where everybody's trying to train in Python. But, in the past, it's been Excel, it's been MATLAB, it's been R, it might be Julia. But the fact is that something like Excel is a tool that will make all students competitive to get jobs. And if you have a really good basis in working in a spreadsheet format, then you have a really good chance of succeeding in the workforce because the tools will change, but the handling of data does not. So we're going to be using these databases that are funded by NSF. They have been around for a long time to try and facilitate the teaching and learning of the basics of working with data. And the thing is that these data are very well curated. They're fairly clean, not completely, which is great as well, because that it provides teaching moments for our students. But it gives them a real world experience of working with professional grade peer reviewed data. So The databases that we're talking about are all run by the Integrated Earth Data Applications, which have been previously known as Geoinformatics for Geochemistry, or GFG, run out of the Lamont Doherty Earth Observatory. And its inception was almost 30 years ago. The databases include EarthChem, which is a synthesis of various databases. There's LEPR TraceDs, which is the experimental petrology database that has also information on trace element distribution. It's a little bit more specialized for that community. And CESAR, which is the System for Earth and Extraterrestrial Sample Registration, which is a database for keeping together metadata about samples so that we don't lose track of what makes these samples important and relevant. So we want to start off the webinar with a little Zoom poll, which Rory is going to launch in a moment. So if you can, when you see the Zoom poll, go ahead and click on however many of these databases you are familiar with, as many as you have heard of, even if it's just in passing. We would like to know. I'll give you about a minute to click on the databases that you have heard about. And I see that quite a few of you are familiar with EarthChem and PetDB and GeoRock. Little less with CESAR, which is understandable, and LEPR, which is very specialized. But I'm very gratified to know that we're working with a group that has at least heard of these resources. And it looks like we have leveled off, so we will move on to the next slide. Okay. So the databases that I'm going to be talking about this morning are primarily PetDB and GeoRock. And the reason that I chose these two is because they were the two original databases in this group of geochemical datasets. They were, and I wanted to talk a little bit about why these were put together. Back in the day, especially back when I was doing my PhD and working with data, we each had gigantic spreadsheets on our computers that had the relevant data that we needed in order to combine with our own research, right? And so we know that in the community, there's a lot of duplicated effort in doing these sorts of things. And in networks, people would share these gigantic spreadsheets for specific disciplinary data sets. And so Charlie Langmuir had the idea, along with several of his colleagues, of combining these efforts to create a database that others could reuse for research purposes, and then look beyond the few samples that they had collected maybe from the ocean floor and combine with a much larger data set so we could get a better picture of what our mantle looked like and what our ocean floor looked like, and we can get a better understanding of the Earth. So with that in mind, Charlie and Al Hoffman at Mines got together to create these two databases, and they agreed on a common vocabulary, a common schema, so that they could share infrastructure, the cyber infrastructure that is required to serve these data. So the good news is that all of these databases that then were born out of this effort, like NavDat and SedDB and Xenoliths, all use the same back end, so they can talk to each other. And so that led to the development of EarthChem, and therefore searching across these databases is very similar. So if we know how to search in PetDB or in GeoRock, we know how to search the EarthChem portal, we know how to search SedDB, we know how to search through a lot of these other databases. So we're just going to touch on PetDB specifically, and then give a little overview of some of the other resources. So I wanted to give you the user interface that you will encounter when you first arrive at PetDB. To get to PetDB, you go to search.earthchem.org, and you will see this really nice user interface, which has a whole bunch of different ways for you to access data. If you go to GeoRock, it's a little bit more simple. You have the homepage, but you can then click Query By, and that will take you to options that are very similar to the ones that you see for PetDB. And to reach GeoRock, you can go to georock.eu. All right, for PetDB, one of the things that I wanted to do was ask you, and if you can please put your answers in the chat, I would love to hear from you what you would like your students to know about data and how to handle it. We want to know what are some of the things that you are interested in doing. Oops. Wait, what happened? I went backwards. Sorry. What are some of the things that you are interested in learning about? Please put your answers in the chat. What would you like your students to know about data and how to handle it? Okay, we hear from David Moak. Hi, Dave. Good to see you here. How to represent natural variation and uncertainty in data, comparing compositions of different rock types, geochemical trends and global rock distribution, data management, very important, data analysis on real data, uncertainties and how they were acquired, right? We can get students to practice their statistics, how to read data, how to differentiate between good data and bad data. This is great. Thank you so much to everybody who contributed. Keep those answers coming. All right, so PetDB allows you to search in a few different ways. So for example, we can start with the location search here on the left. And if you click on location search, you will get a user interface that will let you define a location by drawing a polygon on a map. So for example, you will get a picture of, you will get a map of the world with the topographic data embedded so that you can select the areas that you want to draw data from. So in this case, I created a polygon for the Izu, Bonin, and Mariana Trench because it has a really interesting morphology and it actually corresponds with the change in chemistry. So it's something that's really rich to explore if you are interested in subduction zones. And so when we choose our data this way, and we hit submit, then we will get a little table that tells you how many samples exist of different classification. And you can select all samples if you want your students to really see how these might be different from one another, or you can just decide to choose one particular type, for example, igneous rocks. And so if we choose igneous rocks, then we can explore further by looking at our sample data. So we can look at a list of all the samples within those 3,000 samples that came up from PetDB. And you can see that there's a nice table with metadata that will also come up in the download. So there will be location data, so that along with elevation, and when you see negative numbers, of course, that's depth in the ocean floor. You can see what type of sample the data was obtained from, whether we have glasses, rocks, or multiple types of samples that were explored from multiple types of subsamples explored from a particular sample, and also the taxonomy of the sample classification. We could also take a look at the references that are included in this data set. And so students can actually look at the original data and organize in table form exactly as it appeared in the publication. If we look into clicking any particular sample, you will find that there's going to be a really rich set of metadata, including what are some of the names that this sample has been giving. So in this case, this is an ocean drilling project sample. So this actually corresponds to a very specific expedition and location that is well documented. But in Zhao 2024, it was referred to as the U1496A6F and so on sample. So this is something that is included in the database so that we can potentially match up samples if someone decides that they want to look at that specific sample and request it from one of the repositories. They can combine their data with this archive data. You will see that there's the taxonomy, the type of sample. For example, here, Zhao analyzed a clast, and we can see information about the station at which it was created and how precise the location is. And then at the very bottom, you will see the data that was collected. If there are multiple subsamples, for example, mineral data or melt inclusion, that will also show up in this lower section. So again, we have nomenclature, author, we have description, the research expedition, some of the features of the sample, and the available data. We can also explore visualization tools within EarthChem. So if we go back to the output of what we have in this data set, you see other output options, and that will bring up a dialogue that lets you have a quick visualization. And this is really handy, especially if you don't have a lot of time to have students plot things up, or if you want to do a demonstration in the classroom, you can plot it up fairly quickly. So for example, you can check out the total alkali silica diagram and make this a dynamic map where if we click on any of these data points, you will get a dialogue with information about that specific sample with the same window that you saw in the last slide. We can also download Harker diagrams that can be customized depending on what your needs are, and you can change the colors, you can change the symbol size. So these are all different kinds of outputs that you can have your students look so that they can see whether there's a particular concentration of a composition or a clustering. So you can begin doing some clustering analysis or principal component analysis. And you can also take a look at the outliers, the things that really stand out, so that students can begin to examine whether those are real or they are artifacts in the data set. If we then go to download the data, you're going to get a dialog box that tells you, that asks you to configure the output. And so you can have all of the data downloaded. So you can actually mark everything in the mark all box. You can get only samples that have all of the values that you've defined. So if you want only samples that have the full suite of major oxides, you can do that. But you can also download the data so that it's whatever is available for any sample. And the way to organize these data, it can be one row per method. So for example, if you only want trace element data that came from ICP-MS, you can do that, as opposed to mixing XRF with ICP-MS. But you might want to mix that to see if there are differences in the precision of the data. So one row per sample will give you one sample with all of the data that has been accumulated, regardless of how many authors contributed to that data set. So if one person collected isotopes and another person collected the majors, they will all show up on one row, which is very convenient if you're doing research. So once you have clicked all of the values that you are interested in, then you can go ahead and download your data, and it will look something like this, where you have your coordinates for the polygon defined at the very top. So if you want to recreate this data set at a later time, and you somehow didn't save it at a given point, you can always go back to your spreadsheet and grab those coordinates. And as you can see, with regard to the spreadsheet, we have the sample ID, the references that the data came from, and then all of the metadata associated with it, along with the chemical data that you were interested in. All right, so moving on, there are other ways that we can search the data. We can look at the data by feature. That's one of the other options in the user interface, where you have, for any of these features that are shown on the left, if you click on any of them, you're going to get a slew of different names that then you can choose from. So if you're only interested in data from, say, the East African Rift, you can potentially just look at those. But you can also add all and look at a global data set of the particular feature that you're interested in. In this case, I selected spreading center, so every single spreading center is included in this list. Please be mindful that if you choose a really large data set, it's going to take a minute for it to download. So just make sure that you know that you need to be patient. And if you have limited time and you have a lot of students downloading data, it might be a good idea to download your data ahead of time and have it ready for students to access rather than waiting for the system to process, just in case there are any problems with the database at the database end or at the internet end or anywhere in between. Okay, so we've looked at location and feature. We can also look at sample type. We can look at chemistry. So here we are by sample type. You can potentially look at igneous volcanic mafic rocks. And so in this case, we have everything that is considered volcanic rock. And here I have only added basalts, diabases, tholiites, and alkali basalts. Those are the only types of igneous volcanic mafic rocks that I'm interested in. And then once you hit submit, you're going to get to that interface that shows you how many samples are available. And you can further explore the data. You can look by chemistry. So let's say that you have a very narrow region of basalts that you want to look at. You only want to look at basalts that have between 48 and 52% SiO2 and between 3 and 10% magnesium oxide. You can be pretty sure that those are going to be basalts. So that makes it a fairly clean data set, but then you can delve into differences in trace elements or in isotopes and so on. So if we look also at tectonic setting, which is another one of our options, we can look at these various features and add them to our menu in order to obtain our data set. And the thing is that you can combine as many of these metadata searches, but the more that you add to that search, the smaller your data set will be. And maybe that's what you want. All right, so moving on, if we look at GeoRock, you're going to find a very similar interface where you can query by geography. There's an interactive map, much like you saw in PetDB, or you can enter coordinates to create a square or a rectangle of where you want your data to come from. You can also choose by geologic setting, and there is a list of locations in geologic settings that you can browse. So this is the controlled list that GeoRock uses for classifying locations, and then you can scroll down and choose any of the various options that are there within GeoRock. Moving on, I wanted to talk about something called data to go. Within the PetDB interface, you will notice that on the right-hand side in the middle, there is a butler holding a platter, and that is our data to go icon. The nice thing about the data to go is that these are very specific compilations that were compiled by EarthChem staff. And so that gives really easy access to data sets that are of high significance. So you can just download each of those data sets and play with them, knowing that they are a very carefully curated group of samples. There's a few other ways that we can access some ready-to-go samples. In GeoRock, there is a list of precompiled files that you can access. And so here on the right side, you see a list of the precompiled files. There's a lot more than this, by the way, but I just thought that I'd show you the first 10. And if you click, for example, on the bottom one, Strack and others, and click on Show Expert Dataset, a dialog box or a window will come up, like the one that you see on the left, that will show you all of the information about how these data were compiled. Notice how they very cleverly made it look like a journal publication, and also different ways in which you can access the data. And it tells you how to cite the data set because a lot of work went into this. So we encourage you to use DOIs to cite all of the authors that are included in the data set. so that people get credit where credit is due. The EarthChem Library is another resource that is available within the IEDA databases, and I include the URL at the top. And in EarthChem, you can search for data by method. You can search data by location. You can search by keyword. But EarthChem is a really great repository for you to contribute your own data if you want it to be archived and want to comply with NSF or other funding agency requirements to share your data. So in EarthChem, one of the things that we can do is either submit the data or access it by searching the library. And if we're submitting data, there is a whole tutorial section that I will show in a minute. But if we're searching for data, we can potentially search for expert datasets. And the expert datasets that reside within EarthChem are really convenient because they are, as you would imagine, compiled by people who really know what they're doing. And so maybe, petrology is not your discipline. Maybe it's something else. And you want to have a really nice, clean data set of mid-ocean ridge basalts. Well, you can access those, for example, by looking at the expert data sets, and here are some of the ones that you find in EarthChem. The data set compiled by Connie Class is really excellent. Even though it's from 2012, it probably could use a little updating, but it's a really nice, clean data set that you can look at that has the complete data. So I encourage you to take a look at some of these data sets just by putting in the keyword expert into the EarthChem library. All right, so we're about to take a short break, but before we take a break, we're going to ask questions. I want you to answer what class do you think that you might use these resources in? We would like to know if you're interested in primarily introductory courses, sophomore level courses. Maybe it's advanced undergraduate. Maybe it's combining it with geophysical data at the graduate level. Whatever you are interested in, we want to know. So we'll give you a few seconds to answer this question. And then I will open up the floor to answer your questions about the databases that I've discussed. All right, so we have 24 out of 30 people have responded. So I welcome any questions that you have at this point. We'll just have a couple of minutes to do that, and then I will turn it over to Dory. No questions right now.
Karen, one thing that came in was some people were having trouble reaching the EarthChem portal. You might want to mention that before we move on.
Okay, so folks, the EarthChem portal is a synthesis database that includes GeoRock, PETDB, the USGS data, and Ganseki, which is the Japanese ocean floor database, along with others. And the EarthChem portal is a synthesis, so that means that all of these are actually calling the data in real time from each of these data resources. And unfortunately, sometimes these portals break down. So right now we're having a problem with the EarthChem portal, and it's a really good idea to know what the source databases are, for example, PETDB and GeoRock, LEPR, and so on, so that if you have an activity planned and the EarthChem portal is not working, you can go to the source databases. But the EarthChem portal is really convenient because it has the same features that you would find in PETDB for searching and visualizing, but it also crosses the waterline. So where GeoRock does a lot of continental igneous rocks, and PETDB does mostly marine igneous rocks, in the EarthChem portal, we can cross the waterline and look at that transition. For example, if we're looking at subduction zones, that might be really, really nice to have. So I ask you to be patient because we know that they have been having a really hard time getting the system back up and running because it's a major major breakdown that has happened. Okay, how to read the data? Oh yeah, that's old question. Got it. Any other questions? Okay, what do you think, Rory? Should we move on?
Yeah, I think let's move on to Dory.
Well, what I love is the answers you all put in the chat space when asked about what do you want your students to be able to do and why might big data be useful, um, is something that I have been thinking about. And I have to thank Dave Moak, who's on the call today, because way back in 2005, I was at a teaching petrology conference. And Dave was the kind host of that gathering. And there, Kent Ratajewski and Alan Glazner, all they presented a kind of a little mini class on how to use data in your petrology. And it was the first time I'd ever really thought about big data sets. And since 2005, their work inspired me to start involving it regularly and yearly in my classes. Um, and I think, Karen tapped into this and you all tapped into this as well, that it's imperative for us to do this work because when we look forward, that ability to have quantitative skills and digital literacy is really, really important, I think, in training future geologists and frankly, future global citizens. So, Karen, if you want to flip to the next slide. And when we think about this term data literacy, we could think about it. And this, again, you all tapped into this in your answers. It's searching for data, managing it, making critical judgments about it. And if you want to click one more, when we actually look for a definition for data literacy, you might find it described as to explore, understand, and communicate data. But UNESCO, an international organization, thinks about it as identifying, interpreting, creating, computing with, and communicating with data. And I think it's that second piece, like that second bullet point, that I think is why our work with big databases and introducing students to that and giving them practice time is really important as we look forward. I also notice a lot of you think about using these kinds of things in your upper level classes. And, John, you had a question about kind of sedimentary petrology. There is a SEDDB, there's a sedimentary database of chemical data. And so there are all sorts of ways we can get our students kind of working with it. And I think the more we practice with it, the better. And what I like is like we all think it's important. And if you want to click one more slide, Karen. It turns out that Sharon Mosier, Jeff Ryan, and Chris Keene, in their work with the Vision and Changes document, which is from AGI, where they pulled faculty and students and employers about skill sets that are really important as we look towards the future, that concept of digital literacy comes out to play. If you click once more, it actually was even more important when Gonzalez and Keene put together their report about the impact of COVID-19 on the geoscience enterprise. And in that report, they reached out to educators, employers, and students to think about what skill sets were really important. And I wanted to share with you at least two pieces from this COVID-19 report from 2023. So go ahead and click to the next slide. So one of the questions Gonzalez and Keene did or asked is they asked faculty members, do your students lack Excel skills? And between 2020 and 2021, we're at about 35 to 40 something percent of faculty responding that yes, they thought that that was a weak area for their students. What I think is perhaps even more interesting, if you click to the next one, is that in that same report, when they asked students what students wished they had learned or wished that they had more experience with, they wished for more database skills and they wished for more ability to have time to do data visualization and or mapping and software experience, which is what I love is that students want the same things we kind of want for them. And so with that kind of in mind, and again, still swimming with the inspiration coming from 2005 and Kent's work, I have really been intentional about dosing in experiences with big data sets and Earth and Excel experiences. And so what I thought I would do is I would share with you a couple prompts that I pass along to my students, and share with you a couple of their the ways that they give me feedback and what their responses look like. So go ahead and let's go to the next one. And really, when I do this, I want them working with real data. So we don't have an XRF machine here on campus, so they can't necessarily easily get fresh data that is their own, but they can go search for data that feels like, well, it's real data. And students have increased ownership of that data. I also really want my students to have sharper Excel skills. And this is all work that's kind of coming out of my petrology courses. And I think as a modern petrologist, that role of chemistry and petrology are integrally connected. And I think the modern petrologist has to give a nod to the great chemistry databases. All right, so let's go on to a prompt here. So an example prompt might be gather major element data for basalts from a mid-ocean ridge, a hotspot, and a volcanic arc, and create a single task diagram. And Karen did a great job of setting me up for this one because, again, I can search for these tectonically in any of these databases. And EarthChem or PetDB, for example, they can create a task diagram for these. But what I also think is important is I want students to be able to see mid-ocean ridge, hotspot, and volcanic arc as separate symbols. And so that actually is Excel work because in kind of the EarthChem PetDB database world, all of those would get the same symbol. So to discriminate one location from another, that's Excel work. So let me share with you an example of what a student created. So go to the next slide. And so here is a graph a student created showing three locations, an arc, a hotspot, and the mid-ocean ridge. And go ahead and click to the next slide because I have a question for you all, and if you can help put your thoughts in the chat box. Um, what kind of discussion threads might this graph inspire? So if a student created this or you showed this to your class, what kind of questions might you be able to push them on or ask them? So how could this spark discussion? Now I'll give it a couple moments. And I think you might have petrology discussion threads. You might have data discussion threads. So I'm curious what you all think. I'll give it a couple moments. You could even have graph pickiness discussion threads. Let's see here. Yeah, to John's point, again, think about how do we classify different basalts? Absolutely. Or even describe those basalt sets. Yeah. And again, thinking about why do mid-ocean ridge materials plot in a certain area compared to an arc? Yeah, and that idea of variability. This is kind of a cluster analysis story. Um, right, yeah, and again, exactly that idea of like what clusters, what doesn't. I think it's really interesting because we can also have conversations about outliers. So if you look at this graph down by 42 weight% silica, there's a little lonely red dot down there, and is that real? Or is that something that like what's going on with that dot? How do we reconcile that? And that observation versus interpretation, Rory, to your point, like describing the data is a pure, clean observation, but interpreting it as a whole, like that's the next section in a paper. Um, and again, the idea of like what makes these things vary? The other interesting question that could be asked is that variability that we see honest, or is it because our data set is incomplete? Because if you look, it sort of looks like there's not very many green dots compared to the red smear. So that's an interesting kind of question to kind of pursue as well. So you can see like a simple prompt like this. Again, this is very much in line with what Kent's first exercise experience was. Can really sort of start to spur a lot of interesting dialogues. I want to just, before we don't do it yet, Karen, but before we go to the next slide, I want to show you another student answer for this. But I need to warn you that it might make you a little bit jittery. So okay, go ahead and let's go to the next slide. This is another answer that a student provided. And when we look at this, um, this opens up a whole field of conversations because Excel will make you a pretty graph, but I also really want students to be critical of the graph. So as you look at this image, on the y-axis, here's where the sodium and potassium weight percent oxides are added together. And on the x-axis, that's the weight percent SiO2. But one of the things this student wasn't paying that much attention, and they have plotted line number, not weight percent silica, because there's no way we'd have 1,000 weight percent. And then, so that's a place where if you are watchful of your graph and critical of it, we are starting to train those eyes for our young geologists. So that's one example. And again, you can see the kind of dialogues and threads of conversation it can inspire. Let me share with you another prompt. So if you want to go to the next slide. So more recently, and again, this is beautifully aligned with some of the requests and thoughts that you all had, was determine what kind of basalt dominates at spreading center environments and create a graph to show your findings. So when I use this with intro level but petrology students, this spurs them to think about how do they construct an effective search in one of these major databases. So that's an interesting skill set to kind of hone and nurture. And then what are effective ways to present this data? And I think that that's really important as sort of modern scientists and modern members of the community is how do you share your findings? What's the appropriate way to do it? So let me show you one answer. Let's go to the next one. This is a student example. And I have to say, like, they're not wrong. And I could have told students that tholiates dominate mid-ocean ridge settings, but the student who created this is now utterly and totally convinced. It's not a very exciting graph. It's a giant blue dot, but it makes it exceedingly clear that tholiates dominate. And I also like to talk with them, especially in the petrology world, that it is very rare that pie charts are helpful. This is a place where clearly it's making a case for what basalts are the kings and queens of the mid-ocean ridge hill. The next slide, I want to go ahead and click to the next slide. This is another student response to exactly the same prompt. And because they created a different search strategy, this student only got a database or got a kind of a data pool where all of their results just said basalt. It didn't say tholiatic or anything else. It just said basalt. So they took their chemistries and plotted them on the FeO sort of alkali magnesium graph to look at how do they compare on kind of this basalt discrimination diagram. And I actually think this is a really elegant way to show this data. And also, the student came away with the skill set that enabled them to be able to plot using kind of an Excel template for a triangle diagram. Really great data that I think makes it clear that tholiatic, again, reigns supreme. All right, so let's go to the next example here. And so it's not just scatter plots that we do. And Karen mentioned earlier, we can really get them digging and delving into trace element data. So I'll also send students out to get rare earth data from 3 different granite settings and create a single spider plot. And all of these kinds of graphing ideas are also breaking down the notion that like all granites are the same or all basalts are the same. And I think that for petrology students, that's really an important part of their learning process. So here's an example of a graph someone might make. And what I love is like when students do this, they learn, for example, where granites exist globally. So sometimes they'll say like, oh, we're in Western New York. I'd like to use some Western New York granites. We don't have granites in Western New York, and they find that out very clearly when they draw a little polygon around Western New York and don't find anything. So there's a bit of spatial connection students are making. But a graph like this too, where we have our sample divided by chondrite, means they had to learn how to normalize their data and how to change their Excel graph to a logarithmic profile here. And then we can have conversations about europium anomalies. So there's something going on in these three very different locations, New Zealand, Japan, and Canada, to figure out what's going on with this europium dip. And then why is New Zealand quite different from the other two? These are dialogues and pathways we can start to explore. And the students own the data, they selected where their materials came from. And I think that's really powerful because there's a stronger investment on their behalf. Go ahead and flip to the next slide. I do want to, those are just three example prompts, but I do want to add that there's really, really valuable perks to dosing these into your classes. Um, and Karen mentioned it earlier. It is really important to give our students the ability to practice how to reference data. Um, and actually, what I'm finding is that students are now using these databases as a kind of as a georef alternative. So I had students recently working on rocks from New Zealand, and they wanted to find a new source of data for nickel in some New Zealand volcanics. And so they actually went to EarthChem, drew a box around New Zealand, limited their geochemical response to only data with nickel, and that's how they found new articles, which was kind of unexpected, but a really great way to think about these databases. And I do think that that ability to connect rocks or geochemistry to spatial settings or tectonic settings is really important, and I think is a way to really think kind of in a global way about our kind of petrology world. And I also think, and I know that this work has been successful because I see students using these databases and frankly their Excel skills beyond my exercise, beyond the class. I see it in term papers, but I also see it coming up in like honors theses. So they're looking back to the data as a resource to compare what their materials look like. Um, One of the things that I've been doing as in my petrology classes, I've been doing kind of an informal journal. And one of the prompts I asked them was after one of these EarthChem database exercises, I asked them, did they see it as a moment of adversity? So go ahead and click to the next slide. And I want you all to know that over the past couple of years, in total, about 80% of the students admitted that it was a challenge, that they saw databases and Excel as a source of adversity. And that you might be like, whoa, 80%. But I want to unpack that a little bit. So if you click to the next slide, here are some pretty typical responses when they expand a little bit on that. So the first bullet point says that the student noted that they actually felt really good about EarthChem, that the software or the database was really easy to navigate and user-friendly. Their biggest hurdle was getting the data to Excel. And if you look at the second two data points, the problem wasn't with the database, it's Excel challenges. And so one of the things, and Karen again has done a nice job in kind of laying out kind of examples on how you go searching, um, giving students guidance in how to search and how to do that effectively, and also providing platforms of guidance for Excel really can make a difference in sort of decreasing the amount of stress that comes out of these kind of assignments. So if you look at the third bullet point, it says, in this lab, the videos you provided helped me how to grasp using Excel. And and what I love is they said that same week I had a chemistry lab in which we had to create graphs and my petrology work benefited me. And I think that that's when the experiences we give our students expand even beyond our classes, that to me is a really big win. So what I really want to encourage you all to do and to encourage your peers is like I think there's really great value and actually also easy ways to get our students swimming around and exploring in these databases. And so we'd love to encourage you to do that and then also to share how you get them doing that with the greater community. So if you want to flip to the next slide. What I'd love to do is see if there's any questions that you all have related to prompts or implementation in the classroom. Yeah, so Liz, you've got this question. It says, do they know about how to plot task ternary diagrams? Most of what I do in my class is really Excel based, although the last kind of EarthChem assignment I gave my students, I had them used it as a platform for them to explore some templates for plotting geochemistry diagrams. So there are some great Excel templates that have the task fields placed onto them. And so I gave students practice doing that. Um, I don't cover Python. I know other people do. I do occasionally have biologists come through my class who are really, really skilled with R, and I actually tell them that if they prefer to use R, they can. Most of them would prefer to use Excel, but um, absolutely, there are resources, and I think this is like using these as other alternative ways to plot up data. I think it's really appropriate. Karen, do you have any thoughts about that?
Yes, and in fact, Rory is going to be distributing our resource lists with all the links, but among the links that we're going to be sending out is the awesome list. And I'll ask Rory if he can find that link and put it in the chat. This is a list that is compiled in GitHub. GitHub communities do this all the time. And the awesome list for the geosciences has for almost any subdiscipline in the geosciences, Python modules, R modules, different resources and code that you can use along with tutorials, cheat sheets, and so on. So there's a lot of wonderful, wonderful resources, and fortunately, others have been kind enough to compile them for us. So just know that that's right now in the chat, and that it will be emailed to you as well, and will be part of what's available on the website in perpetuity along with this webinar.
Yeah. And I do want to highlight Dave's comment about having students be critical producers and consumers of data. And I think that's really important because if a student simply draws a polygon around an area and says, show me the chemical data, they could get a huge collection of materials that may or may not be basalts. Um, Around the Mid-Atlantic Ridge, we get xenoliths, there's sediments there, there's metamaterials. So all of that is in there. And I think looking critically at what is in that data pool, I think is helpful. And I really agree that kind of having them reflect upon where did their data come from and also if they have like 30,000 data points, how do they decide to slim it if they do? And I think that that's also part of, I think part of that kind of reflection that's really important. And thanks to Vali for sharing that connection to the CDG Easy, the kit. That's really helpful. All right.
All right,
Karen,
so
I'll pass it on to you.
yeah, we're going to move on and wrap up the workshop very quickly. I just wanted to summarize right here that these databases are good for all of us, right? Regardless of how we're using them, they're good for students, for those who teach, and also for researchers. So this is something that can extend our productivity even when we don't have a lot of money to run expeditions. We can always access data and do some really exciting research from just stuff that is available. So it can really extend our careers. I wanted to point out that there is a resource hub, which here's a QR code, and Rory is going to be putting that link. Actually, I already put the link in the chat. how you can get involved and how you can access resources for teaching that use these various databases. So please make sure that you check that out. Just so that you know, just a little overview of what you might find in the Teach the Earth materials for EarthChem, for PETDB, and for GeoRock. You can see that there's a whole slew of different activities that have existed for a long time. But beyond that, I want to point out that some of these activities were made quite a bit of time ago. So, for example, Kent's activity was made in 2006. It's still a great activity. Oh, so with some help from the coders at Lamont, we were able to put together an addendum in Python that you can access and you can have your students work on, or you can do yourself if you want a step-by-step way of doing part of the exercise in Python. If you want to do something like this yourself, you can use the community contribution tool, which lets you add on to an existing activity while still maintaining, the credit and honoring the work that the original authors put into these activities. I didn't want to end the webinar without mentioning Caesar, because Caesar is a really great repository where you can, if you want your students to explore just the metadata of how you document samples properly, how to also create an archive for your own samples so that that information does not get lost, you can use Caesar for that. I think that there will be workshops hosted by IEDA that will be posted on the CERC website on how to use Caesar as well as Leper. With respect to the future of our databases, the way to keep them alive is to contribute. Submit your data to the EarthChem Library so that others can access it, can use it, and so that you meet your funding commitments. Register your metadata and your samples to Caesar. You can create new activities or contribute to existing activities. And lastly, if you run into any problems, please contact the EarthChem team. You can contact the PI for the grant. She's on every web page. You can go to info@earthchem.org. All of those links go pretty much to the same place. So if you have suggestions, announcements, or you see any broken links, please let them know. So we welcome your questions and feedback. So please try to fill the evaluation survey, which is listed right now in the chat. And I will open the floor up to questions and also let Rory give some concluding information. Any questions?
Yeah, if people have questions, they can put them in the chat or raise your hand. While we're waiting for questions, as we're close to the top of the hour, I just want to let people know that there's another NAGT webinar next week that's focused on developing a sense of belonging for students with disabilities in field courses. And there's a virtual workshop starting in June that the registration is open for now for course design if people are thinking about updating any of their courses or developing new things. So please check out both of those. There'll be links to those also in the chat in a minute here. Again, if anybody has questions, Dave, are you coming on there? Oh, no.
Thanks to all of you for joining us. We really appreciate it. And please contact us if you have any questions. Feel free to email me.
Yeah, or me. And come up with new ideas. We look forward to hearing about them.
All right, maybe with that, I'm going to stop the recording. So thanks, everybody.